A warm welcome to the next segment on advanced process control. I'm Annie Blissett from Royal Haskoning DHV and joined today by Dr. Edward van Dijk, our Head of Research and Development for our Nereda aerobic granular sludge technology. Edward, tell us about yourself.
Yeah, thank you, Annie. I'm Edward van Dijk. I'm a process engineer at Royal Haskoning DHV, and I'm already working in this company for 25 years. And since roughly 2008 involved in the aerobic granular sludge technology. I did my PhD on the aerobic granular sludge technology in the group of Mark van Loosdrecht. And since 2015 I'm responsible for the R&D in Royal Haskoning DHV for aerobic granular sludge. So yeah, that's me in a nutshell. Today indeed we are talking about advanced process control. And we kind of cut it up in 2 or 3 main topics. That's batch scheduling. We're going to dive into that a little bit. That's really hands-on process control. But we're also going to look more into how granules grow in a reactor and how you can control that and what the background is in that. And then finally we're going to look at effluent suspended solids. But we start with the batch scheduling.
Okay, let's go.
So because the current aerobic granular sludge technology is a batch process, we have to think about how to schedule the batch reactors. If we talk about the current aerobic granular sludge technology, the Nereda process, which I'm working on a lot, it's a batch process. And because it's a batch process, you need to think about batch scheduling. And I think it's good to think about the differences between a continuous system and a batch process, because most of the people are well acquainted with continuous process. And I draw a scheme on the PowerPoint where you can actually see a very common continuous system, a UCT process, where you just have an anaerobic part of the process, you have an aerobic part of the process, you have anoxic zones, and then you do settling. And that's a very common setup. You feed anaerobically, you have some anoxic pre-treatment to remove your nitrates, and then you do the main aerobic phase. But that's a continuous system, so you feed continuously and the processes happen at the same time at different parts in the reactor.
So how does the batch system then differ?
That's a good question, Annie. It's basically the same. The only thing is that in a batch system, it's not everything is happening at the same time at different spots in the treatment plant, but all processes are done in the same reactor, and in time the conditions vary. So if you see in the PowerPoint, we start with an anaerobic feeding phase, then we switch back to a reaction phase where we do aerobic conditions and anoxic conditions, and then we end with a short settling phase, and that all happens in the same reactor at the same place basically, but the processes are similar. So that's kind of the main difference between a batch process and a continuous process. Here I drew the Nereda cycle. So that's basically how the Nereda process constantly works. We feed, we react, we settle, we feed, we react, we settle. And that's a constant process of alternating steps in the batch system. Yeah, that's typically for the current aerobic granular sludge process. But yeah, then still most of the time you need multiple reactors because you cannot do it in one reactor. You need to constantly take in influent. So you have a domestic wastewater treatment plant, and then the wastewater is constantly produced. So you need to constantly take in the wastewater. So most of the time you will have multiple reactors set up. So you have 2 or 3 or more reactors to constantly take in influent, and then one reactor is feeding, the other reactors are doing reaction or settling. And then when one reactor is done feeding, the other one can start feeding, and so on and so forth, so that you have still a continuous process, even though you have a batch system. And here is shown a 3-reactor setup. You can also have a setup with 2 reactors, but then you need some way to overcome the time between the feeding phases, and then you can use an influent buffer. So that's also a very common setup for wastewater treatment with aerobic granular sludge. But if you go to very big installations, you can have multiple reactor setup, so you have all the freedom in the world. And we are actually we have built installations with like 24 or 32 reactors. So, and then you have a multiple reactor setup, and then batch scheduling becomes an even bigger challenge. So you have to really think about it up front, how you want to schedule your process.
So if you have so many different configurations and options for how the process is set up, what are kind of the key elements that people need to consider for which choice is right for them?
Yeah, so that's a little bit of a puzzle, and that kind of differs from case to case. But there are some main things where you have to take into consideration. So I was already talking a little bit about the continuous intake of wastewater. And most of the times you need to constantly take in wastewater and keep treating it. So if you have a batch system, you have to kind of configure your system to make that possible. You really want to maximize the efficiency of your treatment process. So you have a lot of instruments and devices in your treatment plant, so you want to really maximize the usage of that. So that's considerations you have to take into account. And linked to that, you have to minimize basically your non-reactive time. So if you have a settling time or a waiting time and nothing is mainly happening in the process, you want to really be in the reaction time as much as possible. So you want to minimize that settling time, for example. At the same time, anaerobic feeding is important for the process because, as we learned earlier in the course, we take up substrate anaerobically in the aerobic granular sludge. So you really want to optimize your feeding phase so that you have the maximum uptake of substrate in the granules. So you have to optimize that anaerobic stage. And because we are discharging continuously also, you have to always meet your requirement. And all over the world we have all different requirements, but we always have to meet them. So you really have to think up front how you're going to do that in your control strategy. And what is also important for practice is that you have to deal with load and flow variations. So it can start raining and you have to take in lots more water. Or you have load variations over the day, for example, with industrial effluent coming into your treatment, that sort of stuff. So you really have to think upfront about how you handle those variations. Then you have to think about scheduling, and maybe I can draw that a little bit. So, in a relatively general setup, you could do, for example, 4 batches per day. So you have a cycle, feeding, reaction, settling of 6 hours, and in that 6 hours you need to do everything. And so you go from 0 to 6 hours, and then you start with a feeding phase. That will be, for example, 1 hour. So you have a feeding phase of 1 hour. Then, for example, you would have a reaction phase of, let's say, 4.5 hours. And then you have your stripping and settling phase. And stripping we will come to later in this course. We call this the settling phase, settle, and that will be at the end of the cycle. And this will be during dry weather, a typical setup, how we do it. As you can see already here, is that if you have that feeding phase, yes, in this part of the cycle, we don't have a feeding phase. So we need a second reactor or a buffer to put the influent to. So you have a second one running also a feeding phase. And that needs to, for example, that can start here with the feeding phase. And then you also get a reaction phase there. And that will continue in the next cycle compared to this. So it will continue on and on and on with the cycles between the reactors. But in this case, we have a mismatch in the feeding phase, like so. So this period, we are not feeding because we have two reactors. And then we need a buffer to still put the influent somewhere. And this would be a general setup for dry weather conditions. In most wastewater treatment plants, we also have rain weather conditions. And then the flow might double, triple, be 10 times as high as during dry weather flow. And then suddenly you have to treat much more flow, most of the time basically with the same load. And then you have to squeeze in those cycles because you have to run much more water. So the feeding phase has to continue faster. And most of the time you then shorten the total cycle time, and you are more feeding and less reacting in the rain weather conditions. Yeah, you can see the example in the PowerPoint, and that's a little bit where the work of the designer starts to think up front about how the scheduling in the reactor will work in the future.
And I guess this example is for two reactors and, of course, needing a buffer for the reasons you mentioned. Then how does that change with the different number of reactors configurations you were speaking about earlier?
Yeah, so there's a lot of things you have to consider there. So if you would have only two reactors without a buffer, that would basically mean that if I just wipe this part, so what will happen is that your feeding phase should be half of the total time. So if you have your reactor 2 that needs to start feeding the moment the reactor 1 stops feeding. And that's because there's no other solution to put your wastewater in. And so if you have a buffer, you can divert your wastewater to the buffer. But in this case, if you only have two reactors, you need to be feeding half of the time of the reactor. And then what is left over for reaction and for settling is not so much anymore. It's only half of the time. So you basically already lose. Oh, I'm drawing this at the wrong spot. But we get the gist. In the PowerPoint, you can see it. So the reaction phase is like much shorter than in the example I drew before. So having only two reactors without a buffer will highly jeopardize your reaction phase, basically. So when you're considering your design, you have to think about this. And in the case of two reactors, a buffer might be very optimal. If you go to three reactors, then suddenly something beautiful happens because you only need to be feeding 1/3 of your time. So what will happen then is that your feeding phase only is 1/3 of the time, and then suddenly your reaction phase can be much longer. So you have much more efficiency in your reaction. And so the reaction phase will be relatively much longer in a three reactor setup compared to a 2-reactor setup. So, and you can see that happening in the PowerPoint, that the fill and draw phase is just much shorter, and you have more relative efficiency in your process. It's even better when you have a scheduling with a buffer and two reactors, because you can see that in the PowerPoint, the feeding phase becomes even smaller. And it really doesn't matter anymore how long you are feeding. You can feed as short as you want, as long as you empty the buffer. And then suddenly that feeding phase is a variable where you can play with without that you need to always be feeding. So I think in a majority of the treatment plants we build, a buffer of some sort plays a role, because it gives you so much more freedom in your batch scheduling that is in many cases the optimal situation.
Yeah, so if to increase efficiency, you're trying to maximize your reaction time, does that essentially make this configuration with the buffer the most efficient setup?
Yeah, it depends a little bit on how you look at efficiency. So I made a small example in the PowerPoint where I just did a 2-reactor setup and compared that with 2 reactors with a buffer and compared it with a 3-reactor setup, just with some general assumptions in the design. And what you actually see here is that you don't gain so much of total volume of your plant if you put a buffer in this comparison. The total volume can be very similar, but the big gains is in the efficiency of the reactors. So if you compare a setup of a buffer with a setup of a reactor is much more complex. You have your diffusers, you have your feed pump, your gutters, your instrumentation. And a buffer is basically a buffer. You have a pump and maybe a mixer, but that's it. So a buffer is much cheaper volume than a reactor. So you want to have that reactor as efficient as possible and most of the time in the reaction phase, because then most of the time you're using the instruments, the diffusers, that sort of stuff. So you gain a lot of efficient volume if you use a buffer compared to a situation without a buffer. So that's the biggest gain. Okay, so the next topic we are going to talk about is selective pressures. And I deliberately called it not selection pressure, but selective pressure, because it's multiple ways we select for granules, and that's what I'm going to show a little bit how that works now. A few years ago, we had a lot of questions about how the granulation works, and I'm showing a photograph here of one of our bigger plants in the Netherlands, the wastewater treatment plant of Utrecht. And we did already multiple startups of Nerida reactors with, we seeded with flocks, and then we tried to grow granules in it, and we always got a little bit of a similar behavior. And we had a lot of questions about that. We always saw like we were starting up a plant and then it was kind of laggy, then nothing was happening, and then suddenly granulation kicked in. And that type of behavior we saw in almost any startup we did. But we did not really understand why that was. So we started to do research to kind of understand that better. And before we dive into what we did a little bit, I think it's good to show what I'm talking about when we're talking about granules. And you see in the slide, I showed kind of the size of the particles in the reactor and the behavior linked to that particles. So what you see in the presentation, I show different sizes of particles, and you see all these sizes in a granular sludge reactor. But different sizes have different functions in that reactor. And back in the days when we kind of made the definition of aerobic granular sludge, we said the cutoff of granular sludge is at 200 micrometers. And if particles are above 200 micrometers, we call it a granule, and below we don't call it a granule. But that was pretty arbitrary, so it's not, that was kind of what they thought at that time. But what we actually see when we do a startup, that you already see a lot of what we call proto-granules in the reactor. Those granules are smaller than that 200 micrometers, but they already have this granular-like morphology. On top of that, we see some flocks, and then slowly, but most of the time suddenly, larger granules start growing into that reactor. And when we see that larger granules growing into the reactor, we get more of the biofilm kinetics we really want to have in our granular sludge reactor, so that we can have simultaneous nitrification, denitrification, that sort of stuff. So, but that biofilm kinetics, they really start to play a role in the reactor if we get granules larger than 200 micrometers and even a little bit bigger than that. So it's really important that we have particles, granules larger than that 200 micrometers, but also those smaller particles play a role in the whole conversion process of ammonia and that sort of stuff. So we kind of need a proper distribution of particle sizes in a reactor for a reactor to function properly. But we really need the bigger ones for the biofilm kinetics. We had all these questions about how granulation works, and we at some point said, let's make a model. We make a lot of mathematical models to describe things in wastewater treatment, but there was no model describing the growth of aerobic granular sludge. So we thought, let's do it. We worked on it for 2 years, together with Victor Haaksman and Mario Pronk at the University of Delft. And we tried to think about what is important for the granulation process, and can we then, if we make a model of that, can we then describe what is happening in those reactors? So we thought, it's important to describe the life cycle of a granule from proto-granule to large granule that breaks up and that sort of thing. We really know that the current readers are plug flow reactors where we feed from the bottom, and that is important. That's how we also invented granular sludge in the TU Delft. And we really wanted to have like the biofilm kinetics with diffusion and all those kinetics. And we already knew that granules are settling at different rates depending on their granule size. So we also wanted to have that in that model. So we kind of made a combined model of all these type of processes to see if we understand what is happening and if we could describe that granulation process. So we made a model setup where we have a 1D backmixing model, so it's just a plug flow describing the plug flow behavior in the reactor. We had a alternating aerobic, anaerobic conditions, like a batch scheduling basically. We put in sludge selection, so as it's known for granular sludge, as you need to waste the top of your sludge blanket where all the flocks are situated and get rid of them. We simulated the breaking up of granules. We also thought about substrate, and we thought, okay, we can do like a complete ASM matrix, but what is important for us is like what the types of substrate that are what we call granule forming substrates, and the substrates that are not granule forming substrates. So granule forming substrate, for example, is acetate, which completely penetrates into the granule. And for example, starch is not a granule forming substrate because you first need to convert it to something that can penetrate into the biofilm. So we made that deviation, and we made a kind of a diffusion reaction model describing the main processes. We also implemented the settling model I developed earlier in my research, describing the interaction between granules in the settling process. So we also put that in this model. So kind of a pretty complex model, but we thought that would help us to describe that whole process. And we also did a reference reactor. I put in on the slide the different important parameters we put in, but it's kind of simulated towards that Utrecht plant with kind of similar biological circumstances, that sort of thing. For sure, a full-scale plant is completely different because you have all these flow variations and Also, when you start up a plant, sometimes the plant goes offline for a while because you still have issues or whatever. So it's not really like mimicking the full-scale process, but we try to be as close as possible to that. And this is the setup we used. And now I made kind of animation of one cycle, what is happening in the reactor. So what you see is now it starts feeding, and you see the colors of all the granules we are simulating changing. That's because they are taking up substrate. So we are feeding from the bottom, and the substrate is taken up by the granules, so they produce PHA. So they convert substrates like acetate, they take it up as PHA. And you see the PHA concentration in the color. And then we go aerating, you see the granules being mixed up. And you see the color disappearing because the substrate is consumed. And then the granules grow a little bit. And if you then constantly do that, you will see what is happening, how the granules are growing, how the granules are taking up substrate and that sort of thing. And we just ran these simulations for a long time, for 100 cycles, 250 cycles, in the end for a whole year, to see what is happening in that year in the granulation process.
So you were able to model granulation with all of these different components.
Yep.
Taking this more into an idealized setting than what you may have seen in practice. Then the next step, I assume you're able to extract some general best practices or rules, approaches that you can optimize granulation further?
Yeah, sure. Yeah, so that was the whole goal, to understand what was driving the granulation process. And the cool thing is, when you make a model, you can actually play with parameters you cannot play with in practice. And that's exactly what we did. So we ran a lot of scenarios, and I put a few in the slides. We had the reference reactor, but we also looked like what happens when we get rid of the plug flow feeding, of what happens when we get rid of the preferential settling of the larger granules, and what does the sludge selection do when we don't waste flocks anymore, what happens then, and so on and so forth. We could play also. In practice, you cannot say that large granules settle at the same speed as small granules, but in a model you can do that. So you can see what the effect of that differential settling velocity is, and that really gives you the insights in what is happening in that reactor. So we run a ton of scenarios. These are the important ones I'm showing here in the slides, but and that really accelerated our insight in the granulation process. And what we actually did, because you have a model, and I come to that later, describing really accurate what is happening in practice, then we try to make a more abstract description of the mechanisms influencing the granulation process. And we came up with 6 different main mechanisms for granulation. And the first one is really the feast-famine process. That's already known for years that is important. You have to have a feast. The granules take up a lot of substrate and an abundance of it, and then a famine period where they don't get fat, but they burn their bacterial fat, the PHA, and grow on it. And that is really an important process to grow those granules. And actually, what is really important here is that because we separate uptake of substrate and the growth on the substrate, and it's in 2 separate stages, the feeding phase and the aerobic phase, then there's like an infinite difference between the substrate uptake rate and the growth rate. And if you, for example, would feed aerobically, then suddenly the growth rate becomes larger than the diffusion rate, and then you get all these fluffy flocks. But because the substrate can first penetrate the whole granule and then we start aerating, then the granule starts growing from the inside out, and that really helps to grow the granules and prevent fluffy growth, basically. So really important. The second one, that is the selective wasting, and that's already there from the beginning of, if you look at the first paper on aerobic granular sludge, it's about selective wasting. You have to waste the flux and keep the granules in the reactor, and do that every batch, every time, keep doing that. And then in the end, you only are left over with large granules. And that's really important, to always keep throwing away those flux. At the same time, those flux always also play a role in the conversion process. So you need them to have, for example, in the nitrification process, they really play a role there. So while in the lab scale we can run on completely only granules, in full scale you will see that the flux also play an important role. But in the end, the granules are important to have simultaneous nitrification, denitrification, and really make your total volume smaller. So you have to keep throwing away those flux, because if you stop doing that, the granules will disappear in the end. This third mechanism we identified is really the flow regime. So you need that plug flow feeding. And that's because if you do plug flow feeding, especially in a batch system where you kind of displace the cleared effluent with influent, you really have high concentration gradients. And if you have a high concentration gradient, and that gradient is between the bulk and the inner side of the granule, that gradient makes sure that the diffusion of substrate into the granule will be fast, because you start at a high concentration, so you kind of push the substrate into the granule. And if you would have a mixed feeding, and we simulated that, then suddenly that bulk concentration is lower. It's much more difficult to get the substrate into the biofilm, and that really slows down your granulation process. So that flow regime with the plug flow is really important for the granulation process. The fourth mechanism is really the substrate type. We know there are substrates you cannot grow granules on, and what we also saw is that you have to have a certain minimum level of granule forming substrate. So we're talking about, for example, acetate, but also substrates that can anaerobically easily be converted into acetate or propionate. And that if you don't have that kind of level of easily biodegradable COD, then granules won't grow, because then there's much more growth of flux, because components like starch will lead to more to flocculent growth, and then that balance between flocculent growth and granular growth will be off, and then it will be extremely difficult to grow granules. So it's really helpful to have a lot of granule forming substrate, and at some point you don't grow granules anymore. Then the balance is off. One of the more important mechanisms, at least from this study, that was not known in literature yet, is the selective feeding. And so we knew the selective wasting was a thing, but selective feeding kind of helps you a lot in the granulation process. And with selective feeding, we mean that the larger the granule, the more food it will see. And if you feed from the bottom, then all the fresh substrate comes from the bottom of the reactor and goes up. If you come from a mixed situation, the larger granules will have a race to the bottom. As they have a race with the smaller granules, and the larger the granule, the earlier it is at the bottom of the reactor, the more fresh influent it will see. So this is really an accelerating process. The larger you become, the more food you get. And that selective feeding, if we take that out of the equation in the model, you will see that the whole granulation process does not accelerate anymore. So you still get granules, but they stay small, because the larger you become as a granule, the more diffusion limited you become, because you have less surface area compared to the small ones. So it's actually not beneficial to be big. But because of this selective feeding process, it is beneficial to be big. So this process really makes that the granules can grow bigger than a few hundred micrometers. So this really helps in the granulation process. And the last one is a little bit a strange one, but actually breaking of granules helps in your granulation process. And what we already saw in practice, if you cut granules and you look at them under the microscope, you often see that there's like a shell of an old granule in the core of the granule. And what really helps, and we try to simulate it a little bit, is that if you have a granule that breaks up, then all those pieces of the granule are new seeds for new granules, because new biofilm will form around that old piece. And what we saw in the simulation in this case, that after a year, almost 20% of the granules in the reactor originated from a piece of an old granule. So even though they are old and breaking up, they're still bringing life to new granules, basically. And that, we think, is a really important part of the life cycle of the granule, that it kind of, after it dies, it still is a seed for new life. So yeah, breaking is a good thing in this case.
And first question, is this a natural process, or is this something you can also influence?
Yeah, so I think by itself it's a natural process, so it will happen. So we never see granules of the size of a tennis ball. So they sometimes they are maybe 10 millimeters. That's really, then you already have a really big one. But what will happen is at some point it will start rotting at the core, right? So and then there's no base anymore. It will break up, and then it depends a little bit on how your reactor functions, like how big are your bubbles, how much shear is in the reactor. That will determine how big the granules will get their steady state, or the biggest one. So that differs also between installations. But it is a natural process, and it's part of it, and it really is important that they break up at some point, and that also parts of it will be spilled, so that there's room for new granules to grow and to accumulate phosphorus and that sort of thing. So yeah, it's really important.
And then I guess we started from looking at this in practice, so how granulation occurs in actual installations. Now you were able to model it.
Yeah.
Is this something you see accurate in practice, or are there deviations?
Yeah, so if you do scientific research, you sometimes have this aha-erlebnissen, or how do you say it in English? It's like eureka.
Eureka,
Eureka. Yeah. And I think in this study we had this major eureka moment, because at some point we did a simulation, and we really saw a huge similarity between what comes out of the model and what we saw in practice. And if you see at the presentation and recall how it looks like in practice, we kind of have a lag period.
Yeah, the lag, yeah.
Yeah. So you see that it takes like a few months, a lag period in this case, and then suddenly the granulation kicks in. And you have these flocks, they are kind of present, and then the small granules grow in, and then the large granules grow in. And we see that over and over again happening. And then at some point we got the first simulation results, and we really saw a similar effect. And when we started this study, we really were not looking for this lag phase, granulation phase type of thing. But it really was remarkable that we could really mimic that practical process. And yeah, that was our eureka moment. And we started thinking about it, so what is happening here? And it's kind of, when you start with flocks, those proto-granules, they really start growing quite rapidly. But they don't, they are stuck in the matrix of the flocks. They don't get loose. They don't, when you start settling, they settle with the flocks. It's like one bulk settling process. And it really takes time for those proto-granules to be big enough to start separating from that bulk settling process. And the moment that starts happening, then suddenly they start growing larger, because then the selective feeding kicks in. Those small granules that can separate themselves from the sludge blanket, they will see more food. And then that process accelerates itself, and then suddenly you see those big granules grow into it. So it's really like a stochastic process, like it's a matter of chance. Do they go over that boundary where they settle faster than the bed? And then if that starts happening, then suddenly they go all in, and then they grow big. And so yeah, and that's what we kind of learned looking at the model. Like, oh, okay, so this is happening in practice. So yeah, that's the really cool things of doing these type of models. If we look a little bit deeper into what we saw in the model, so we started with our reference reactor with only flocks. And if you start, and you first start with building up your selection pressure. So you start with flocks, they settle not that well. So if you really start selecting for granules immediately, you just wash out your whole sludge blanket. So you have to be careful with that. And then you build up your selection pressure, in this case until we meet 3 grams per liter of biomass in the reactor. And then we kind of start increasing that pressure, so towards 4 or 5 meters per hour of selection pressure. And what you see is then a drop again in the total biomass concentration, but then it's waiting for that improvement in your granule size distribution until that stochastic process of those small granules becoming bigger to start separating themselves. And then you see them growing into the matrix. And then the small granules basically take over. And then you just grow and grow and grow until you meet, in this case, 8 grams per liter of total biomass, which was our target in the simulation. And you then start spilling also your granules a bit. And yeah, and that's basically what you see. So at some point, the medium-sized granules are the dominant factor in the reactor in this case. So like granules of 1 or 2 millimeters. That's what they take over. Yeah, and that's basically the whole process. So with those 6 mechanisms I'm showing here in the diagram, you basically you can describe the whole granulation process, and especially that granule forming, non-granule forming substrate, and that selective feeding. That was really for us an eye opener. That really is important to get your granulation process running. And yeah, so I hope that kind of explains a little bit how you can grow granules, but also how you can control that. So what type of process parameters you need to control to get your granulation going. Okay, the next topic we are going to talk about is degasification, or basically effluent suspended solids. And I think the photograph on the screen is really an example of what we don't want, but what we were having at some point on a regular basis. And we really needed to look into the effluent suspended solids process to get rid of those suspended solids. And now I'm going to tell a little bit about how that works and how we solve this. So if you think about it, it's a little bit of a scale-up issue. And when you have a new technology and you want to scale it up, you will inevitably run into issues because of scale. And if you look here, we started in 3-liter lab reactors. They're this high, and yeah, we feed with standardized substrate at standardized temperatures, and then it kind of was working the whole process. We scaled it up to pilot scale reactors. Those were a little bit less than 2 cubic meters total volume, a little bit higher already. And then we started to scale up to full scale. And we are now running installations with up to 300,000 cubic meters of reactors, which is like a huge scale up compared to that original 3-liter lab reactor. And one of those scale issues we ran into was the effluent suspended solids. So if you look at how we scaled up, then we used to have like the 3-liter lab reactor. Now we are running full-scale reactors of a reactor volume of more than 10,000 cubic meters. The water depth of those lab reactors is like 1.2 meters, something like that. While in our full-scale reactors, we can go, we start somewhere at 5 to 6 meters and we go up to 10, 12 meters. So it's much deeper. If you look at how we produce our cleared effluent, in the lab reactors, we never bothered about effluent. So we do SBR operation, we call that. And so we spill our effluent together with the selection spill, and that's it. Well, one of the key elements of the Nerida technology is that we can feed and decant at the same time, and we have a separate sludge wasting step in the process. And being able to feed and decant at the same time really makes the reactor smaller. But that's really different from how we invented it in the lab. Also in the lab we have really standardized influent. We have high concentrations of acetate. While in practice you have some acetate, but you have all these other types of substrate in the influent. And the consequence of that is that we still have lots of simultaneous nitrification, denitrification in the process, but often we need a little bit of post-denitrification. And that's really different from how we do that in the lab, because we never bothered about post-denitrification in the lab. And that all leads up to our problem. And if you look a little bit at a lab reactor, and I can draw that. So if you have a Nerida reactor, it's basically a reactor where we feed from the bottom, as we discussed in the previous part. We decant from the top. Most of the time in a gutter of some sort. And you can imagine that if you are feeding and it's domestic wastewater, there are all these floating particles in it, like fat or other debris, or you can have all kinds of stuff in your wastewater, and stuff that can already float. And if you're feeding from the bottom and extracting from the top, particles that float will just go out with your effluent. So what you will see with those particles, they rise to the top and they will just wash out with the effluent and actually harm your effluent quality. So we already knew from conventional wastewater treatment that floating scum can be a problem, and there's a really easy solution for that. You just place a baffle in front of your effluent weir, and that will prevent of floating stuff flowing out of your reactor. And so that's kind of step one in improving your effluent suspended solids. But still, that was not enough. And what we actually saw is that under certain conditions, we saw kind of floc activated sludge particles or flocs also flowing to the top of the reactor and still going out with the effluent. And yeah, that was kind of, we were wondering what was happening with there and how that was happening. And we already quickly understood that it was some sort of degasification we were dealing with. And we already knew from activated sludge plants that can be an issue. We all know the stories about operators saying, hey, there was a thundercloud, and then suddenly there was this sludge blanket on top of our clarifiers. And that's because a sudden drop in air pressure can give a degasification of nitrogen gas in those situations. And we quickly thought, oh, maybe this is also happening here. So we started to look into that, what was happening there. And I think it's good, before we dive into that I tell a little bit about the Narita cycle and the conversions and what we are seeing in the reactor. And I already plotted something on the screen, but maybe it's nice to actually draw that here. I'll quickly wipe this. So if you look at the measurements we have in a reactor, so we draw time there and some sort of concentration over there. We start the cycle with the feeding phase. So we feed influent to the reactor. Most of the time all the sensors are more at the top of the reactor. So when you are displacing from the bottom, you don't measure anything yet. So for example, if you see your ammonia concentration, that will be effluent quality during the feeding phase in the measurement. Then we start our aeration. We start our reaction phase, so we start with aeration. And what you then see in the reactor is what is happening is that you actually see an increase of your ammonia concentration. So it goes up because we are mixing the reactor and we kind of meet the maximum concentration. It's the average concentration after feeding. And during that aeration period, it will go down until we meet our requirement. And then we stop and we start the settling phase. Like so, here we start the settling. What you will also see during that aeration is we start building up our nitrates. So that's also low during the feeding phase. And then we start producing nitrates because we are converting ammonia to nitrate. But what will actually happen is that we see less nitrate back than what we would convert from ammonia because our simultaneous nitrification, denitrification. And then most of the time we kind of start, we have a post-denitrification phase to get rid of those nitrates we still build up into the water phase. What you actually see, if we zoom in also on the presentation, is that gap, what we have here, like we produce nitrates, but we converted ammonia. So we end up something like here, that this part, what we already removed, which we don't see back in nitrates, that's what we call the simultaneous nitrification, denitrification, SND. And you see that in the presentation, we see that you have, if you have a granule, we were talking about biofilm kinetics. What will happen is that the outer side of the granule will be aerobic, but the inner side will be anoxic during the main aeration. And the result of this is that if we are converting ammonia to nitrate in the outer layer of the granule, in the inner side of the granule, we can already convert it from nitrate back to nitrogen gas or dinitrogen. So that will be happening already during the main aeration. But I draw it here as simultaneous nitrification, denitrification. Actually, it's even bigger than what we think it is if we look at the sensors, because we know already from a research done by Mario Pronk somewhere, I think in 2010, is that granules, aerobic granules, have the capability to absorb ammonia. And what in practice will happen is that part of the ammonia you fed to the reactor will be actually disappeared from the sensors because it's absorbed to the granules. And that actually means that this peak is higher than we think. So actually that is roughly about 20%. So the peak is always something like 20% higher than what we see on the sensors. On top of that, we also have organic nitrogen. You also don't see that back in the sensors, but it is hydrolyzed during the main aeration and it's converted in the end to substrate and nitrogen gas, and that can be up to 50%. So this peak is even higher than what we see. And so if we look at the simultaneous nitrification, denitrification, and also what is converted in the post-denitrification, that's what I call in the presentation total nitrogen removal. That is quite a bit, and in the example in the presentation, in this batch we remove roughly 20 milligrams per liter, or even a little bit more than we remove that from the wastewater. And there kind of is the problem we are dealing with here. So if you look at the presentation, you see actually that if we remove about 25 milligrams per liter of total nitrogen from the wastewater, part of it is converted to biomass, roughly 25%, something like that, will be incorporated in new biomass. And the rest of it is nitrified and denitrified during the process. So in this case, roughly 20 milligrams per liter of nitrogen is converted to nitrogen gas or dinitrogen. And there a little issue arises. So if you think about solubility of nitrogen gas, I drew a diagram of that. You have a solubility of nitrogen gas, and if you go over that, small bubbles of nitrogen gas will form in your water phase. If you aerate a reactor with air, you will strip out that nitrogen gas. Nitrogen gas will dissolve back into the bubbles, and you will remove it from the water phase. And you can lower the total nitrogen concentration in your water phase with that. And if you look at this diagram, I plotted here the solubility of the concentration of nitrogen as a function of the temperature. The top line is like the maximum solubility of nitrogen gas. If you go over that, small bubbles of nitrogen gas will form in the reactor. And the lower line is what you can reach if you strip out all the nitrogen with air. And that area in between is kind of your deficit, which is not actually the correct word, but we are used to talking about deficit in aeration. But it's the buffer capacity of your reactor. And as you can see here, that's only like 4 or 5 milligrams per liter. But we converted 20 milligrams per liter of nitrogen into nitrogen gas. So there is kind of a mismatch there. For sure, it all happens, or a lot of it happens during the main aeration, and then you can strip it out immediately. But still, in some situations, you will probably reach that maximum solubility of nitrogen gas during your normal operation. There's a little help there, because we built our reactors pretty deep. And what you can see in this graph is that actually the solubility of nitrogen gas goes up with water depth, because the pressure increase, and we go from, like, let's say 1 bar to 1.6 bar. And so the solubility really goes up. So at the bottom of your reactor, where during the feeding phase your sludge blanket is, you have more solubility, and that kind of helps you in this problem. But still, it's kind of a difficult. You have the water depth mixing during aeration, stripping process. It's kind of a complex process, and it really depends on the situation if you run into a problem here. But we really try, like in the previous topic, we try to simulate it, and in this case it's pretty simple because it's a physical process. And physical processes in this case are much easier to understand than the biological interactions and stuff. So we put it into a simulation model to try to simulate what happens when you are doing your Narita cycle. And if you look at those concentrations we talked about earlier, like 20 milligrams per liter of nitrogen gas produced, you can safely assume that over the whole depth of the reactor, we are at the maximum solubility of nitrogen gas at the end of the cycle. And if you then start feeding, you push your water up, and then the pressure drops locally because you push the water to the top of the reactor, and then the solubility goes down, and you suddenly are producing all these little gas bubbles that take with them little particles of sludge. And that's what you see when you see such a scum layer on top of your reactor. And that's not what you want, right? So, there was pretty much an easy solution for that, because we knew that we could aerate to strip out nitrogen gas. So if you do a small stripping run at the end of your cycle, you could basically lower that concentration profile, and you see that in the different graphs. So if you do a stripping run for some time, you can lower the whole concentration, and then suddenly you can start feeding safely without having any bubble formation or very limited bubble formation during the feeding phase. So yeah, that really helped us to understand what was happening. Yeah.
And here again, you went from kind of the theory behind it to simulation, modeling, now back to practice. I mean, there's different installations all around the world of different depths. For example, you see that same pattern across the process in practice as well.
Yeah. So in this case, we could really validate our research in our research facility, and what we actually did was we ran like two batches, one with a stripping phase and the other one without a stripping phase. And you can see the effect back from what we simulate with the model. You see that in practice. So if you don't have that stripping run, you see the turbidity really going up during the feeding phase. And you see that in the graph at the upper line, or the dots, you see the turbidity going up during the feeding phase. That's because you push your water over the solubility boundary. And if you have a proper stripping phase, then you don't see that happening, and your total turbidity is much lower than if you don't have that stripping run. So we could really validate that model in our research facility, and we implemented that stripping phase in all scheduling for all Nerida. So it really helps us to improve the effluent turbidity. On top of that, we also did a test with the baffle. And what we also saw is that actually getting the baffle in really helped in getting that effluent suspended solids lower. And in this case, we were pretty consistently between 5 and 10 milligrams per liter of suspended solids, which is kind of the market standard for effluent suspended solids. So yeah, that this research again really helped us understand the process, but also to improve on the performance of the granular sludge process. So yeah, so and after implementing, this is the same photograph as that I showed earlier at the start of this part. Yeah, you can go to very clear and very beautiful effluent, and it really helps to understand what is happening to improve the process.
Great.
So that's basically it.
Yeah, thanks, Edward.